Okay, so this is question number 9 of the magnetic fields homework booklet. So in question number 9, what we have is we've got this arrangement down here. So we've got the whole thing is in a vacuum, and it's deflecting protons into a detector. So the protons are coming along here and they're being deflected into this detector, and to do that then we're going to use a magnetic field within this square here. So within the square the field can be assumed to be uniform and it's zero outside it, so we only have to think about the magnetic field inside this square here. And we're told that the motion of the protons is in the plane of the paper. What that means is that the protons aren't going to they're not going to go away from you, not going to come towards you. It's like they're confined basically onto the surface of the paper. They can't move up or down. So the very first thing we're asked to do is to sketch the path of a proton as it moves through this magnetic deflector. And somewhere on there we need to basically label, we need to draw an arrow and show the direction of this magnetic force. Well, we know that if we have a charged particle, which a proton is, because it has a charge of a relative charge of +1, that if a charged particle goes into a magnetic field, then basically it'll describe a circle. So the way it gets from here to here is in a circular path like this, and because it's going in a circle, then the force is always directed towards the centre of the circle, which must be up here. And so therefore that's our path, which is worth 1 mark, and our force is towards the centre of the circle, and we've labelled it F, and that gives us our 2nd mark. For part B, we're asked to state the direction of the magnetic field that causes this to happen. So again, this is a Fleming's left-hand rule thing. So we need to decide in which direction the current and the force are. Well, the force we've got. So the force is fairly straightforward. So what I'm going to do is I'm going to think about the direction of the force just as this proton enters here, because then I know that the current is going from left to right, because this is a positive particle, so the current's going from left to right in this direction. So that's the way that I would point my my second finger. I know that the force in this case is in this direction here, so I will point my my thumb in that direction, and if I keep my second finger in this direction, my thumb in this direction, then on my left hand my first finger must be pointing into the paper, and so the magnetic field, we would say, goes into the plane of the paper, so it's going inwards. In part C, we're now told some extra information. So we're now told that the speed of the proton as it enters this deflector is 5 times 10 to the 6 meters per second, and we're told the flux density of the magnetic field is 0.5 teslas. We want to calculate the magnitude of the magnetic force. So basically we use this equation. So this is our standard equation for calculating the force on a charged particle in a magnetic field. That is the force, B is the magnetic flux density, Q is the charge of our particle that's moving inside the magnetic field, and V is the speed or the velocity of the particle. So we're told all of these numbers in the question. B is simply 0.50. Q is, because it's a proton, is 1.60 times 10 to the minus 19, and the velocity is 5.0 times 10 to the 6. If we do it on a calculator, we basically get 4.0 times 10 to the minus 13 newtons. In terms of marking points, you get 1 mark for the right numbers and 1 mark for the right answer. And then finally for part D, if we exchange this particle for an electron, we want to know what's going to happen. So if the path were that of an electron, it had the same velocity, we would have to make 2 changes to the magnetic field so that the electron entered the detector along the same path. So if we go up here, if we had an basically we have exactly the same picture, but instead of this being a proton, we're now exchanging it for an electron. So what we must have is, because an electron is a negative charge, what must happen is, if you think about Fleming's left-hand rule, the currents now change direction. So if the current changes direction, but the force is still in the same direction, which it must be for the particle to go into the detector, then we must swap the field around. So the field must now be in the opposite direction, it must come out of the paper. In addition to that, the second change that we need to make is to the magnitude of the field. In other words, the strength of the magnetic field, or the flux density. Because if we keep the same flux density, because force is mass times acceleration, basically if we keep the same size magnetic force, the acceleration that the electron is going to feel, because it has a smaller mass, the acceleration is going to be much bigger. And so therefore it's going to make a much tighter circle, so it isn't going to go in the detector. So therefore we need to make the magnitude of the field smaller. And if we do that and we make it approximately 2,000 times smaller, then what you'd find is that the electron basically made the same circular path that the proton made in the picture. So that was question number 9 of the magnetic fields homework booklet.